Good morning, everyone. This is MMI711 Sequence Models in Multimedia, and this is actually week 11. We're going to talk about deep trackers, visual trackers, which are based on deep learning methods. This will be this week's topic, and actually we are going to be doing some paper analysis. So I've got a bunch of papers that I've shared with you up to class with the parts highlighted like this. You can download them from up to class. So let me begin. So last week we talked about kind of the latest achievements in sequence modeling, which are the transformers. And actually those achievements are we are witnessing new achievements as of today, like the swing transformer. We had the transformer, then we had the vision transformer, then we had the swing transformer, which was something in between convolutional networks. Actually, we did not cover the swing transformer, but it's something very new. I've mentioned about it. You can find it. It's a ICCV 2021, last month's best paper at ICCV. We're going to be talking about a different title this week. We're going to be talking about tracking, because tracking is also a sequence problem. Okay, this is transformer still. I don't know why. Okay, so let's first talk about the definition of tracking. Okay, tracking is by definition a sequence-to-sequence problem. First, let's try to understand this. Why? The input is for a visual tracker is a set of images, and the output is the pixel location of the target. So let me put it this way. Let me draw the problem definition. So imagine these are the frames which are in nature a sequence. So like a sequence and frames, right? And we've got something in the image, for example, this something in the image is moving, so it has a position like x1, y1, x1, y, x and yn, and in the middle it's xi, yi. This is the ground truth of it. So what we do in tracking is we have a tracker. It provides a vector of these positions. So this is the estimated x1, y1 estimated, and x and yn. As you can see, the input is a sequence and the output is also a sequence. So which makes this problem a sequence to sequence, many to many problem. Well, it's simple. I mean, it simply makes sense. This problem has been studied in the literature like for the last 50 years maybe, because it's a fundamental surveillance system. You have to track targets in military electronics. You have to track pedestrians in surveillance cameras, etc. And before deep learning, there is a very strong literature for it, which goes before deep learning era. And actually, since this problem has been studied, profoundly in the literature, those who worked on the problem are aware of its challenges. And the main challenges are occlusion, drifting, association, I'm going to talk about it, and appearance of change. These are the four main problems, but there are other problems as well. So these problems, there's a nice figure here, I found it on the internet. It includes these guys, so occlusion changes or abrupt effects in motion, similar appearance effect, appearance changes, disappearance effect, another appearance change, effects of frame quality. This is a problem in real life because you usually want to do tracking on a, I don't know, CCTV camera, which is usually low resolution. Illumination changes, another appearance change problem, because what you're trying to track is have some pixel values on average, and the illumination changes in the room. All the appearance model is lost. Again, an appearance change problem. Camera motion effect. Well, okay, you're tracking a target, but are you assuming that the camera is moving or not? clutter the background. For example, this is a car and it is in the background, there is a tree. It's also moving, and maybe the pixel values of the car and tree are quite similar and they just get mixed up. And similar effects. So all the problems can be categorized under these titles. And the association, I didn't talk about it. For example, I'm tracking two cars. If both of them were black cars, that would have been difficult to track because I have to re-identify each car at each frame. So which one was the first car, which one was the second car. So tracking is a difficult problem. I've studied tracking myself for years when I was working at a company. And it has other problems as well I didn't mention here. For example, we were studying a tracking problem on missile heads, missile seeker heads, in which the missile just flies towards a target. You have the problem of scale as well, guys. So I should maybe put another name here, scale. Because at first, your tracking starts with a sub-pixel. You launch the missile from 10 kilometers. And by the end, it is 100 by 100 pixels. You have to be robust to that scale change. So it's a very difficult problem. Very difficult problem. It's still being studied and it's still a cutting-edge state-of-the-art problem. And from domain to domain, the challenge of the problem changes. Tracking a car, autonomous car problem, this type of tracking is different than this type of tracking. They are similar, indeed. They are still in traffic, but there are many pedestrians and there's many clutter in the background. So depending on what your environment is, tracking problem, the challenges of the tracking problem changes. I mean, the weight of the difficulty of different challenges in this tracking problem changes. So in the end, what you're doing is you're trying to overfit a problem domain. I mean, you're trying to find a tracker for a missile seeker, which most probably would not work best for a tracking problem in autonomous driving. So this is our problem. Conventionally, and before deep learning, the tracking problem was attacked as mainly, I mean, there are tons of methods, zillions of methods, but if we look at them, I mean, from a far distance, what we see is they create an appearance model for the objects that are tracked. So this is an object. So the object, for example, this is an object. Let me get one object here. I'm tracking this object. So this is an object. I model this object with an appearance model. So I get all the appearance information from this model. And some cases, for some methods, both this tracked target and the background as well, because background needs to be modeled as well in most cases, so that you could differentiate the model from the foreground, which is the target, and the background may change as well when the camera moves. This is a CCTV camera vision, so most probably the camera is not moving. It could be doing some pan tilt movement, I don't know, but usually these kind of cameras are fixed cameras, so the background doesn't move, doesn't change, but the background can change, and there's light changes, there's illumination, it can start to rain, and there will be reflections on the ground, so it's difficult. The problem is difficult. That's why you need to model the foreground and the background. And while doing that, what they also did, the conventional trackers were updating this model with the incoming frame. So you have a model for the target to be tracked or the targets to be tracked, different models, and the background, and you're updating them with the incoming frames. So the problem itself has a nature which requires a history of events, right? So tracking is a continuous thing going on. I mean, while you're tracking a target in vision, it doesn't have to necessarily be vision, but in radars or even in sound, they don't jump. They should be continuous. So the history knowledge, so saying that the guy was here in the previous frame, so it should be somewhere near. is type of a history information, which makes it quite suitable for recurrent neural networks. So first I'm going to be talking about recurrent neural network trackers. But in the end, our current best sequence modeler transformer is not a recurrent model, but a sequence model, but it can be used for tracking as well. And I have very new 2021 papers, two 2021 papers to show you today. Okay, and the nice thing about these trackers of the pre-deep learning era was they were transparent. So they were handcrafted. You handcraftedly design an appearance model for your target. So I'm going to just define the elements of the appearance of this target as, I don't know, a histogram of gradients, and you track that histogram of gradients within the region in the next frame. So that was a handcrafted design. Good. So it was transparent. We knew when it failed and why it failed, and we knew when it was successful and why it was successful. For that matter, it was something good because we kind of knew when it would fail. So an algorithm before the pre-deep learning era, we would have said, well, it is raining, so most probably our algorithm is going to fail because we did not choose the handcrafted features robust to an effect like rain in the image. We knew that. However, this can change. I mean, we can implement a tracker in recurrent neural network world. So how? So recurrent neural networks, with their ability to model sequences, have this potential to solve all the problems visual trackers face, all of them. I mean, I'm not saying that they will definitely solve it, but they have the capacity to solve it because they can adapt themselves to the background. They can hold the history of the background. They can hold the history of the target, its position. They have this capacity. I mean, this is week 11. You already know this. So RNN-based trackers, what they do is they estimate the target's bounding box by directly regressing it from the RNN hidden state. So regression is like finding a value out of something. So using the RNN hidden state, they solve the problem of regression to output the position of the target in the next state. And the nice thing about RNNs is you can get multiple outputs from an RNN. So you can make them solve multiple target tracking problems without any handcrafted design as well. So the premise is big. I mean, they promise many things, but can we operationalize them for this purpose? Actually, in the last decade, people have been working on this. I would say not in the last decade, in the last 5 years, because the usage of RNNs have been popular after 2014 and 15 with the Badanow's and Sutskever's encoder-decoder models with attention and without the attention. You remember them. And people have started working on working on these RNNs for the tracking problem. And there are many papers. I mean, I'm going to provide some details of these papers today now, but this is not a literature survey. This is like an introduction to a literature survey, okay? So after you've seen these approaches, which, I mean, they will be important papers from the literature like ICCDC, VPR papers, I think you will have a solid idea about how RNNs can be used as visual trackers and why visual tracking is a perfect sequence problem. Okay, so this is basically our problem. Objects will be represented, objects will be detected. This is called tracking, detect by track. We don't have to track by detect. We don't have to do it this way, but it's an approach. Then we assign the identities and we track the objects. Either you do it pre-deep learning style with some strategies and handcrafted features and models, or you feed them to an RNN and you construct the model as a sequence-to-sequence problem, and with the image input and with an end-to-end model, you have the positions of multiple objects. Let's see. I'll start with a very simple approach. Maybe the first approach that would come to everybody's mind. I mean, using an LSTM, CNN plus LSTM. However, a sophisticated version of this idea. How? These guys do, and these guys from China and Belfast, UK, by the way, adapt an LSTM to decide where the object is. So for that purpose, they have a CNN plus LSTM where they feed the visual signal. I'm going to talk about this part, don't worry, to the convolutional layers and the LSTM. Okay, I'm going to open the paper. So I'm going to do a different practice today that I've never done in this course, but what I usually do in my graduate courses towards the final weeks. I go over the papers and just show you the parts that I highlighted. The parts that I highlighted, you can find them on AutoClass. After I highlighted them, I saved them and I uploaded them to AutoClass. So these are the important parts of a paper. So this is like a way to read papers very quickly. And in time you get that skill. I'm sure you will. If you look at the abstract, there is this sentence. Recently it says it is ICPR paper in 2018. So these guys worked on this paper in 2017, we could say. Now what they say is recently matching-based tracking methods, such as Siamese networks, have shown remarkable speed and superiority. You don't know this. Siamese networks, matching-based tracking networks. These are deep learning models. So you would ask me, why did I not start with these models? Because these deep learning models are not sequence-based trackers. They are not sequence models. However, I'm going to talk about them after this paper. So after this paper, I'm going to take a step back. I'm going to talk about what matching-based deep learning trackers are. I'm going to continue sequence modeling. But I think the first example should be a sequence model, and which is this object adaptive LSTM network for visual tracking. In this paper, they propose a novel object adaptive LSTM network, which can effectively exploit sequence dependencies and dynamically adapt the temporal object variations in constructing an instructing model for object appearance and motion. But simply what we have thought, simply how this visual tracker should work. The LSTM will be used to associate between the frames the appearance and the motion. How? Okay, that was the promise, right? How? And they say they don't only use this because that would be the vanilla approach, the naive approach. They propose an efficient proposal selection. What proposal selection is, guys, as you can see, before this CNN LSTM part, where they mention in this paragraph, in this sentence, they are talking about this part, where they get the appearance and just using the LSTM with every frame, because the LSTM states are being fed to the next frame. They are getting a history of the appearance and the motion. But this would be a naive approach if we have fed the entire image frames. They don't. What they do is they select some regions from the image. So they start with a template. So they say this is the target. Think of it like at the first frame, somebody shows the tracker the target. Well, this is an approach in target tracking. For example, if you have a missile, that was the problem I worked with. For some missiles, the operator selects the target and pushes track, starts the track. It means with the first frame, you have a ground truth of the target, which we call the template, okay? So what this black box does is, we are going to get into that black box, don't worry. It chooses some regions as proposals, because the appearance of this target will match many boxes around here. And those boxes will have an order of scale as well. I mean, maybe the target got larger, and in the previous frame, in the next frame, because this was the starting frame, and there comes the next frame, maybe the camera got closer to the target and the target is now larger. So the proposals here are a list of regions, rectangle areas regions of interests, ROIs, with from different places of the image and from different scales. Maybe one ROI is 40 by 40, the other one is 45 by 45 pixels. I don't know. So these are selected proposals. They are called proposals. If you've worked with YOLO, object detection models, we have proposals there as well. So a proposal is like a region of interest, which is a possible region that we will be working on searching for. And these proposals are only fed to the convolution layer, not the entire image, to make the job of the CNN plus LSTM easier, to make its job easier. How to select them? They provide a Siamese network architecture here. Let's get back to the paper. And what they say is, when this paper was published, they say, to the best of our knowledge, this is the first work to apply LSTM network classification in visual object tracking. Think of it so. People have been working on this stuff, but these were, I don't know if this is true, but this is an ICPR paper, so it's a very quality conference. So what I'm trying to say is, in 2017-18, LSTM-based trackers were, they were the early versions. We had the early versions. So this is kind of a new topic, deep learning trackers. Okay, so let's get into the details of the tracker. That's the same figure which I've taken from the paper. We have a frame. We have a template starting with the first frame. We have a similarity function that creates selected proposals for us. Then each selected proposal is fed to the LSTM layer. This is a sequence of proposals, varying number of proposals. We can feed them, any number of proposals we can feed them. And in the end, the LSTM layers will decide where and what size of a ROI the frame is. So this will be the new template then. So this will be the new template being, sorry, just couldn't do it. The new template being fed here. So this goes on like this. So very simply, we've designed a sequence modeling problem for a tracker. Okay, so there's a little related work. If you like, you can read it if you're interested, but I'm going to jump into the important parts. First, an important part for the LSTM part. What they do is they design the training part suitable for online tracking. This is something they must do because tracking is a very, very, sophisticated problem. During this, for example, this guy, I don't know what kind of a video is this, but imagine this video is just taken by a drone. The camera was not fixed, it was a drone flying over this motorcycle guy. And think how the background would change when the drone is just flying over it. So the LSTM states will have to adapt to these frames and the background very quickly. So a single offline training would not be sufficient. So instead, they design an online tracking. That's why I say this is a sophisticated CNN plus LSTM tracking network. Because in the first version, I wouldn't do online tracking. What they do is a sort of online tracking where new target positions need to be located successively when new frames come after another. To fit with this tracking task, they use the LSTM network to evaluate the proposals in each frame. So it is like they use, I'm going to get like this. So in order to effectively utilize this sequence-specific information, they train the LSTM online using training data from the video itself. So it is like training is applied in an online fashion. In each frame, the LSTM is always trained. This change of states is also accompanied by a change of weights. So it is not only the states that change, also the weights are changed. So at each frame, you make a kind of forward step to get the new ones, to get the new location. Then using that forward step, you make a backward step to update the weights as well. So I believe actually tracking is also a problem where online learning is a must that you have to apply. It's a very good idea. They published nice PR, and it should be a good idea. Okay, so in this manner, the loss directly comes from the current classification results. They do a classification, and what they do is a regression, by the way. Forward pass, that's the result. Before getting to the next frame, they do a backward pass to update the weights. Very nice idea, right? But something that you can also think of. I mean, if you study a problem enough, you can publish anywhere, in my opinion. So, specifically, however, you may ask, what happens in the first frame? Because in the first frame is like where the training begins, right? Because in the first frame, we don't have anything. They do some sort of offline training. So in the first frame, the LSTM layers have some specific weights to start with. However, the LSTM hidden state is 0. How to split the LSTM hidden state? So what they do is they get the template before feeding it to the here for the forward pass. They feed it only this template to this convolution layer and the LSTM, so that the initial state of the LSTM will not be zeros, but something that depends on the first template. This is at the first frame, so that the training starts with a proper state that relates to that template. So specifically in the first frame, they initialize network state with the original target appearance. Then they use this initialized network state and training samples from the first frame to do their classification plus training network. That's how they train it. Very good idea. I mean, something that you can easily relate to and apply it. Well, I like this paper because it was an example of online training. Any LSTM-based training network, the architecture could be different. This idea could be applied. I mean, you can apply this idea if you're interested in deep learning-based trackers. By the way, guys, if you're doing a PhD, deep learning-based tracking is a hot topic. I strongly recommend that topic to my students as well. Okay, one of you is already working on deep learning-based tracking in their masters, so I'm not advising it to him because he's already working on it, but in general, it's a good topic. So what about the search region? So we know how this guy is implemented and how it's trained and how sophisticated it is. So what about this part? What they do is a similarity learning model is utilized to select a high quality proposals by comparing the target template to the search region. So we have a target template, we have a search region around the place where it was before in the previous frame, and we select some frames of different scales. How to do that? What they do is they use a Siamese network, guys. This past proposal selection, they explain. So they talked about the literature recently, Siamese networks. This is a famous Siamese network. I'm going to be showing that paper, don't worry. A good trade-off between speed and accuracy they talk about. What they do is this network provides a similarity between two input signals. So let me show that Siamese network, guys. I was already there. Siamese network. So this is it. It was by Oxford. This is the fully convolutional Siamese networks for object tracking. So it was, you have an image, you have a template, you feed them to some convolutional layers, and you convolve them, and you have a heat map in the end. So it is like what parts of the initial image this template should belong to. Stronger it is, the heat map will higher values. The lower, I mean, the lower probability is lower values. To train a network like this, Siamese architectures have a specific loss function, something about the contrast of the image. So I strongly recommend you study Siamese networks if you're interested in deep learning trackers, because before sequence-based, RNN-based deep learning trackers, for a couple of years, it was all about Siamese networks, because Siamese networks was a specific type of deep learning network which can be used for matching. So Siamese networks are not deep tracker networks only. Siamese networks are for matching images. I mean, they say for object tracking, but Siamese networks, what Siamese networks do is they do matching between two signals. You find a similarity between two networks. Okay, so it is like a convolutional filter which you can learn, an advanced convolutional filter. That was it. I mean, so this was after this paper, the same group, just Valmadre, as you can see, Valmadre. The same group just improves this idea. It's a CEPR paper in 2015, I guess. I don't remember. So, but the idea is the same. So they provide a heat map. So this is the network they use. This is the network they use. So what they do is, at the output, they have some proposals. So similarity learning function provides a heat map, and using the heat map, you select some proposals, guys. And it's being fed to the convolutional layers. Very nice idea. And in the end, in the result of the paper, they have these location error threshold for, these are called precision plots in tracking. If you're on tracking, these are kind of the de facto standard for evaluating the results in a tracking study. And these are some, this is object tracking data sets from object tracking challenge, benchmark. We can find the details of the data set here. And they just compare their results with other papers and etc. Okay, as you can see, they are not the best, but they are good in speeds, but yeah, there's a trade-off for their study. Okay, so this is the first paper that I wanted to show you. Any questions about this object adaptive LSTM paper? Any discussions, any comments?
Can I ask a question, Hocam?
Please, please.
I want to ask that in the CMS networks, there is a heat map you mentioned, but that heat map is, I mean, only 23 by 23, yeah. I think, yeah. Right? So how they compensate the, I mean, the maybe I can mention it as quantization error, because the image is at very larger scale.
Very good question. I mean, it's a very technical and detailed, very good question. Well, I think, are you asking how in general do they compensate it, or how these guys compensated it? Because
I'm asking in general, actually.
In general, okay. Let me start with these guys. As you can see, using the heat map, they select some proposals. So it is like, this is making the job for the actual tracker easy. So this is just a helper, an auxiliary system. So it is not doing the real job. The real job is done by this guy. So this guy will know where to look. This is important because, I mean, you may think that this is useless, but when the camera moves abruptly, Siamese network helps you to say something like, okay, in the previous frame it was there, but in the next frame it is somewhere around here, it says. And it does it in a sophisticated manner when the background changes as well. So it is still useful in its architecture, needless to say. In general, the story is the same. So the heat map will provide you a location. However, the heat map, the quantization error needs to be corrected with some sort of filtering. In original trackers, it was a convolutional filter, finding the exact location using the exact resolution. In this example, it is a convolution layer plus LSTM, but you're right. So only this network will not be sufficient to, I mean, perfectly localize the tracker, but it will give you a solid idea. So I understand your question. In the end, you're asking, well, this is very coarse. It's a very rough output. So why do I need it? Because in tracking, I need a very precise output. Well, the job that this guy does is not the exact localization, but trying to figure out that abrupt changes in the background and the foreground. Because between two frames, maybe there is a strong motion blur, which your tracker or your correlation filter will not handle. This guy can handle it. So this is the coarse localization you may think of. This is a coarse localization. This is the fine localization. Answer to your question?
Yeah, hocam, thank you. So you mean that the CMS network is the part that is the similarity learning function part?
Yeah, exactly. Exactly. In this paper, if I failed to mention it properly, exactly. This is the CMS network. Actually, it is written here. Please check the paper.
Okay, thank you.
Test proposal selection is the similarity selection part, and they use the Siamese FC. And that Siamese FC is this paper, actually. Okay? So,
Okay, thank you.
sorry if I failed to put it properly.
Thank you so much.
Okay. Well, this is a very nice example because it's a very clear example and also sophisticated example. It uses Siamese network for nice proposal selection. It uses convolutional layers and LSTM layers to provide the next state. It holds the history in an LSTM. It applies online learning. Well, very sophisticated. I mean, it's a 2018 ICPR paper. I mean, we expected it to be sophisticated, but it is kind of the sophisticated version of the vanilla idea that you can think of, because we are going to provide new ideas now. This would be the first, the CNN plus RNN would be the first thing to think when I'm applying a vision tracker to sequence models, wouldn't it? Other questions? Good. I love paper discussions, guys, by the way, because paper discussions is like going to a conference. Okay, but you can only do it once or twice in an actual course. Anyway, okay, let me continue then with another study. But that was a good idea. What about we using, instead of using CNN plus RNNs, we could use a LSTM variant, which is conv-LSTM, which has the potential to model both spatial and spatial-temporal dependencies. To train a filter, as you can see, the title is Recurrent Filter Learning for Visual Tracking. Okay, these guys kind of take it one step ahead and feed the image directly to an RNN model. But this case, and they use conv-LSTMs. You know what conv-LSTMs are? Remember when we were discussing LSTM variants, we went over different types of LSTMs, and conv-LSTMs were like convolution layers where the weights had a history. So the weights had a recurrent connection so that they could change themselves with the incoming inputs. So kind of a good idea for us. But why filtering? Why conv-LSTM? To understand this question, actually, we should get back to the previous studies of trackers. Actually, in 2012, there was a famous tracker, which was called MOSSE. It was an abbreviation, MOSSE tracker, by a guy called Bolme et al. It was a CBPR paper, guys. This is not a deep learning tracker. This is a pre-deep learning era tracker, that's why. So it doesn't include deep learning. What it does is, so I mean, you can, maybe I should show you. This is blame, not blame, it's blame. The name of the guy is a bit strange. So it is this paper, guys. What they do is, guys, so let me draw what they do. Let me draw what they do. I'm going to visit the old tracker because it's an adaptive correlation filter tracker. This will help you understand what the new tracker is all about. So the Bolme, the previous correlation filters were, you have frames and you have a template, okay? And you are trying to find where in the image this template will fall into. Okay, it's going to be here, you say, if this is the frame. Okay, to be able to do this, you can use, for example, correlation. You find the correlation of this template all over the image, scanning all over the image. But if you had a specific type of filter instead of applying correlation, imagine you convolve the image with a specific filter, not the image itself, a filter. So imagine I obtained a filter from the image, a filter. When I apply this filter to this image, not the template itself, the filter, I find the image, and with each incoming frame, I update this filter. These are called adaptive correlation filters. And the best idea of adaptive correlation filters was that paper that I mentioned, just showing you, the Moses by Bolme et al. They learned the filter. So instead of learning, they use some Fourier transform methods and some optimization techniques. Just read the paper. It's a fantastic paper, by the way. And it's very good, working very good for background clutter, because we have used that in many models when I was working for the company. Because when I was working for the company, I was working on tracking, basically. In this paper is like a deep learning version of adaptive filters. So it is trying to learn the filter. I'm going to go over the main figure, don't worry, in detail. You will understand exactly what I'm talking about. So let's start with the basics. A time step T, a CNN, this guy, feeds an image, a template, sorry, this is a template CNN. And this is the current frame. So we are trying to find where this template is in this frame. And it's going to provide us a response map. So the maximum value of the response map, this part, will be my location, right? Again, a small map, as you can see, a rough map, because it cannot find a better one. So this is not a very fine tracker. It's a coarse tracker. So it's going to give me not a very fine localization of where the target is, but maybe a moving one. If we could see the actual output of the tracker, maybe the rectangle around the tracked object will be just trembling, moving so fast. But for some problems, this is not something to worry about. Maybe I need a coarse tracker. I just want to see where the target roughly is. But for some problems, for example, when you're tracking the laser, which would just do a medical operation on your eye, you need a very good localization. But for this one, it is not. It's a coarse tracker. Let's see what it is. So the details of it are written here, but I'm going to jump to the paper. Recurrent filters. Okay. So recurrent filters, visual tracking, CVPR paper. So in this paper, they propose a recurrent filter generation method. The filter is generated and updated. Why a filter is updated, we'll get there. They directly feed target's image to the recurrent neural network. So they don't have a Siamese network for region proposal. This is an end-to-end model. And the training will be end-to-end as well. Okay. The tracked object in the subsequent frames will be fed into the RNN to adapt the generated filters to appearance variations of the target. So the appearance variations are being learned. So some paper, you have to do it when you're trying to publish a CVPR paper. You have to make your contributions very clearly to convince the reviewers, because you got only one chance for the reviewer to see it. And usually I see this in the last decade CVPR papers. They put their contributions very clearly one by one. They list it. And what they say is, we propose a novel recurrent filter learning framework that captures both spatial and temporal information of the sequence for visual tracking, and does not require fine-tuning during tracking. So they don't use online tracking. They say that we don't have to use. So they put it as a good side. Maybe it's a good side, because in computation-wise, it will be easier to do it. So the spatial temporal information sequence for visual tracking is held by the CNNORNN LSTM. Okay. And the other parts are not actual contributions, but they're trying to sugarcoat it. So that's what I would want to do as well. So that's the figure. So the aim of the network is, the output of the network is a filter to be used by a simple tracker. So the network is trying to learn this. It is going to be convolved by the output of this is the frame, convolutional layer, CNNORNN LSTM. It will be convolved by this. So the output of this network here is a filter, just like Moses filter. It's going to be convolved with the thing coming out of here, and I will have a response map. So let's go over this figure. It will make sense when we go over it in total, I mean, entirely. So I've got the template. So this is a type of problem where at the first frame, I have the template. I feed it to the first RNN, which they call the eCNN. Let's call it the template CNN because it kind of gets information from the template. Okay, so we have some features here. This is not a common LSTM. This is the feature. So this is like the actuations. Okay, actuations here. The actuations are being fed to a conv LSTM. As you can see, the template is fed to the conv LSTM because when it's all over for the first frame, I will have the new position of the target from this response map, right? And using this response map, I will get the new place from this frame, and I'm going to be feeding it to here. So this will just go on and on and on. And every time I'm feeding a new template, the conv LSTM will have the chance to update its dates so that the appearance model of the template is learned here. So this conv LSTM is like keeping the appearance model. So this is like, it's more like the previous tracking methods, pre-deep learning or deep learning tracking methods, where the models we have used are replaced by deep learning techniques. So the appearance model is implemented with a conv LSTM. So these are the self states and hidden states, and you just map them. So this is self and hidden state, and they are being fed to the next state. So when new comes, it's going to be this guy, it's going to be this guy. So we have at conv LSTM, we have a filter, the filter. And I've got the search image, another convolutional layer. Let's call it the frame CNN. They call it SCNN. And I've got another actuation. The correlation between this actuation and this filter gives us the response map. This part looks very much like Mosse, guys, because Mosse learned the filter by some not deep learning methods so that we had the response map. These guys have the response map using this learned filter by convolving it, this learned filter. And it's going to be here, it's fed to here, and it runs all around. So it's quite simple. I mean, compared to the previous version, the network is simpler for that matter. Okay. So let me get my notes. There are some important parts. Initialization of the memory states. Whenever you have a network, how you initialize them are very, very important, guys. And they've got some tricks. Actually, they don't mention their tricks very clearly, but after reading the paper, I have some kind of guesses. So to start the recurrent filter learning process, this part, you have to initialize the filters, right? We need to first initialize the memory state of the conv LSTM using the exemplar target from the first frame. Okay, so the initial exemplar target E0 is input to the eCNN to generate an exemplar feature map. Okay, so examples, the first target is fed here. So the exemplar feature. Then this feature is fed to some conv layers to create the first cell and hidden state. Guys, these networks are not a part of the actual network here. So these are not a part of this guy. So these networks are for only initializing the hidden states. So how to train these networks? I read the entire paper. They don't talk about it. But I kind of guess what happened. I'll try to explain it the way I understand it. What these guys did was, they did not first do this. They did not do this specific initialization. So in my opinion, I'm guessing right now. What they did was, they trained this network, and for the first frame, they used the zeros as initial states. And what they realized was, it took time, a couple of frames, for these conv LSTM weights to settle. So for the videos, for the tracking samples, where there was, strong motion in the first frames, it failed. And they started looking for a way to overcome this problem, because if you fail in the beginning frames, you kind of fail the entire tracking sequence, right? So it is an important problem. What they did was they trained the network with easy examples first, where the target was not moving, so that they had the conv LSTM. And they recorded the conv LSTM cell states and hidden states for each template. So they did some training with some results. And during that training, they had some recorded cell state and hidden states for each template. So this is like a supervised learning stuff right now. So if I wanted to learn what kind of a cell state or hidden state I need for this template, I have some recorded cell states and hidden states for the exemplar targets during my previous training. For the correct ones, they've constructed this network. They trained this network in a supervised manner using the templates and their corresponding cell state and hidden states they had in the previous training of the actual architecture. Then they used this for initializing the first state, and they've seen that when they did this, they kind of failed less when the first target was moving. I mean, in the first frame, the target was moving or the camera was moving strongly. They don't mention this in this paper. CVPR papers are 6 pages, so it is kind of what I'm guessing they did, but that is what makes sense, guys. So it is also a very nice paper, guys, and they've got very nice solutions they don't entirely talk about, but apparently this is another idea that you can easily apply to deep visual trackers. And this is the conv LSTM. As you can see, this is an LSTM where we have convolutional boxes before the sigmoids and 10 inches. Okay, any questions about this paper? This is another nice example. Any questions about this paper? Okay, then